Sorry. I will repeat what I said before, because I didn't start recording. Let me start our today webinar. Gregory Fleshman is absent today, and I will run the webinar. My name is Alexey Kuznetsov, and let me introduce you our today's speaker, Mykola Gordovsky. Mykola obtained first degree in astrophysics in Kiev University, then got a PhD in solar plasma modeling in Bradford University, worked as a postdoc in Sheffield and Manchester. His main scientific interests are plasma modeling, including solar and laboratory plasma, using MHD, kinetic and hybrid methods. He is also interested in solar and stellar magnetic field observations, solar spectropolarimetry, and solar radio observations. And today his talk will be on the mysterious topic unresolved magnetic fields in the solar photosphere. So, Mykola.
Okay. Can you can you see my screen? Yes.
Yes.
Okay. And it moves. Yes.
I
can change slides, so it's not just.
Not yet. Yes. Now it changed.
Right. Okay. So I will start. I probably can speak Russian, but because you are recording and because I'm not sure I will be able to explain everything in Russian, I'll speak in English. So the topic is unresolved magnetic field in the solar photosphere. It's part observational, part theoretical, but the theoretical part is also very observationally oriented. It's not my main research. It's actually what I did probably during my master degree in Kiev. But there is a growing interest to magnetic field in the photosphere and generally growing interest to the lower atmosphere, especially during solar flares. That's why we decided basically sort of revitalize this topic and do some research. Another reason for revitalizing this topic is actually there are new or forthcoming solar telescopes, particularly telescopes like the KIST, which will have some UK involvement. So that's why we sort of were trying to do some work on solar spectropolarimetry with the aim of diagnostics of the lower atmosphere. So that's the outline. So I'll make a very brief introduction, and then I will talk a bit about small-scale field diagnostics in a almost quiet photosphere, and then I will talk a bit about flares. So there are a couple of papers which sort of important for this presentation. The presentation is based mostly on these two papers in bold, Gordovsky and Lizitsky in 2014 and Gordovsky, Shellick, Brown and Lizitsky 2018. And if you want an introduction, a nice introduction has been made by Sami Solanki, well, more than 20 years ago, but it's still quite good introduction. So the main point of my presentation probably, and well, it's not an original result, but that what we observe is not a magnetic field. What we observe using magnetographs, let's say if you take magnetic field using from the Hinode magnetogram, it's not magnetic field. It's a magnetic flux per pixel. Yeah. The thing is that magnetic field, photospheric magnetic field, is very homogeneous on scales which are smaller than the resolution of most solar telescopes. And we are talking probably about length scales of tens of kilometers, while most widely used solar telescopes have resolution of about 100 kilometers, sometimes more. I mean, perhaps nowadays the most widely used solar telescope is Hinode, of course, and its optical telescope resolution is almost 200 kilometers. So would definitely under-resolve smallest scales in magnetic field structure. This is not new. This is very not new. It has been suggested, this idea has been suggested almost 50 years ago. I think it's mostly attributed, it's normally attributed to Jan Stenflo and colleagues, who showed that magnetographic measurements made using different spectral lines with different magnetic field sensitivity, or lambda factors, which are sort of sensitivities used in Zeeman, determining Zeeman splits. They are different. Basically, spectral lines with higher magnetic field sensitivity normally show lower signal. And this has been interpreted basically as a result of presence of unresolved strong magnetic field, like on this sketch on the left. And we get this effect basically due to so-called saturation in magnetographic measurements. In case you don't know what is saturation in magnetographic measurements, it's basically, well, magnetograph measures magnetic field by measuring difference between Stokes I plus V and Stokes I minus V profiles, or basically by measuring Stokes V amplitudes in different places, in the wind of spectral line. And if the magnetic field is very strong, so Zeeman splitting is greater than the width of spectral line, basically the magnetograph may not notice the very strong field, simply because Zeeman components corresponding to small fields, they are well beyond the range of, well beyond the original profile of spectral line. And on the right, lower right panel, you basically see how different spectral lines with different lambda factors will react to different very strong magnetic field. Yeah. So lines with very high magnetic sensitivity, they saturate very quickly. So basically their signal and what we would see as effective magnetic field, they drop at some point. The ultimate goal of what we're doing in this study, well, in these two studies, is measurement of what we call an intrinsic magnetic field. So we assume that the structure of magnetic field, yeah, unresolved structure, is at least two components. It has at least two components. So most of the magnetic flux is formed by this intense magnetic flux tubes with very small sizes, definitely smaller than a resolution of a telescope, and they are embedded into much weaker sort of ambient magnetic field, or almost zero. And we will use two main terms. So the first term is this real, or sometimes intrinsic magnetic field, or sometimes strong magnetic field, or sometimes subtelescopic field. And another parameter we will use will be a filling factor. In simplest case, it just shows a fraction of the pixel area occupied by or penetrated by the strong magnetic field. So what we observe normally is this BF, or observed magnetic field strength, And there is a very simple relation between fill-in factor, real field, and observed field. So fill-in factor is a ratio of observed field to the real field. And the aim, ultimate goal, will be to estimate the real field or to estimate the fill-in factor. So why is it important? Why do we need to know the subtelescopic magnetic field? There are things, so basically there are areas where subtelescopic magnetic field structure is actually unimportant. One of them is actually coronal magnetic field reconstruction. When we are doing reconstruction, what we are interested in corona, where beta is much smaller than 1. So magnetic field will be force-free or maybe potential, right? And in this case, what we're interested in is actually magnetic flux or magnetic field at, let's say, at upper boundary chromosphere of the chromosphere, right? Where because at the upper boundary of chromosphere magnetic, gas beta is already much smaller than 1. Magnetic field is basically redistributes. It's not anymore affected by plasma flows. So what we measure as a flux will be very close to magnetic field at this boundary. However, if we go a bit deeper, where beta is close to 1 or higher than 1, magnetic field is much more structured. And it might be important for things like magnetic field energy, for time scale, and for measuring electric field and current. Recently, people published several papers, for instance, trying to measure how current density changes at the photosphere during flare, or how magnetic field energy changes at the photosphere. And these parameters are strongly dependent on alpha. So if we measure flux, the magnetic field energy density, for instance, will be proportional to 1 over fill-in factor. And characteristic time scale will be is normally proportional to L. I mean, characteristic length scale, and which is in turn proportional to square root of alpha. So alpha, basically fill-in factor, is very important for these things, for energetics, for currents, and for evolution at the photosphere. So what we did 2 pieces of research. One is dedicated to diagnostics of intrinsic magnetic field and diagnostics of fill-in factor during in more or less quiet photosphere. And this has been done using combination of MHD modeling, MHD modeling of magnetoconvection using Muram code, developed about like 15 years ago, combination with a radiator transfer code called NICO. Basically, we have quite realistic model of, oops, can you hear me?
Yes.
Yes.
Okay. Something just happened. Okay. So what we did in the first research piece was we combined MHD simulations with radiative transfer simulations. By MHD simulations, I mean MHD model of magnetoconvection in the photosphere, which provides us with very realistic structure of the photosphere at very high, with very high spatial resolution of about 1 kilometer. So it gives us basically 3D distribution of magnetic field. And then we use a radiative code basically to get Stokes parameters, basically what we would observe with a high resolution telescope. And then we can, of course, degrade this intensity maps to lower resolution and see what we would see with more or less realistic telescope with finite spatial resolution, right? So first of all, let's discuss what we, let me show you what we get in MAHD simulations of magnetic convection. So basically what we would expect to see if we had a telescope with very high resolution, or if we could actually measure a magnetic field at the photosphere. So the left panel, the line, dashed line on the left panel, shows a histogram of magnetic field at the top of the photosphere, measured with very high resolution. So basically, spatial resolution is equal to spatial resolution of the model. The most interesting thing, of course, is that the spectrum is not smooth. There are definitely two very prominent peaks. One peak is around 1 kilogauss, and another peak is very close to 0. So basically, the magnetic field distribution or magnetic field value spectrum is not smooth. It looks like it has two more or less distinct components. So basically, there is actually like strong magnetic field and very weak ambient field, which can be sort of ignored because it is very close to 0. So that's what statistical analysis of this simulation show. Another thing is that what we see, so here on the left panel shows actually a magnetic field map produced by the simulations. What we see is very close to what we normally see with in observations, actually. So magnetic field is concentrated at the boundaries of granulation cell, supergranulation cell. The size of the cells is a couple of megameters, which is actually quite close. It's very close to what we normally see. So on the right panel just shows the same, but with degraded spatial resolution. And if you compare it with typical magnetic field map obtained using HINO, it will look very close. And the values of magnetic field are also very close. So for degraded map, we normally have magnetic field, typical magnetic field is just hundreds of gausses, and the maximum field is about kilogauss or slightly higher. But the most interesting thing, of course, is this histogram and this two component magnetic field, and it has an implication for effective field measured using a with let's say a magnetograph. So the panel on the right shows again analysis of this magnetic field map, and it shows a plot of effective magnetic field values measured with low realistic resolution versus fill-in factor. And there is almost, these things are almost proportional. So effective field is almost proportional to the fill-in factor. And this, of course, should be expected because there is a formula just below the right panel. So effective field is a product of real field multiplied by fill-in factor. And if the real field, the strong field, is almost constant, you will have you will see this direct proportionality, basically almost a straight line. Another interesting thing, of course, is that there are two populations of magnetic fields. So red dots show quite strong field, which is almost proportional to the fill-in factor values, and blue dots show very low field, which has almost no, well, maybe it's slightly proportional to alpha, but you can't see it well. So basically, the field is very weak. These two populations they're physically separated, they're spatially separated. So the red field, the red dots, they correspond to strong field at the boundaries of convection cells. And the blue dots, they correspond actually to the convection cell. So magnetic fields, very strong magnetic field is concentrated at the boundaries. So actually these two populations can be separated using Doppler shifts, of course, because normally pixels corresponding to the granulation cells, they show some blue shift. It's basically material is there is some upflow, and boundaries normally have downflow. So this strong field should also correspond to red Doppler shifts. Right. So how do we measure this intrinsic magnetic field or filling factor in observations? The most widely used method is the so-called magnetic line ratio. The idea is very simple. So the magnetic field is measured using two different lines with different magnetic sensitivities. And the magnetic line ratio is commonly introduced as magnetic field measured using line with higher sensitivity to that measured using line with lower sensitivity. And these four panels, they show calibration curves for different pairs of spectral lines, which are commonly used for magnetic field measurements and for diagnostics of small-scale field. Basically, you see how this MLR value will change depending on the value of intrinsic field. Different curves at each panel show basically correspond to different widths of spectral lines, and this width is normally determined mostly by microturbulent velocities. So basically, it's calibration curves, and using these calibration curves and knowing the width of spectral line, knowing effective magnetic field values measured using two spectral lines, you can estimate filling factor or the real magnetic field. However, there is a problem. The problem is that the most widely used pair of magnetic lines is a 6301-6302 pair. It's set of spectral lines corresponding to neutral iron, and they're widely used mostly because several international telescopes, such as HINODE, uses them as main spectral lines for magnetic field measurement. The problem with this set of spectral lines is that, of course, for using magnetic line ratio method, we need the two lines to be formed very close in the photosphere. The problem with this 6301, 6302 pair is actually formation depths are quite different. So on the right panel, you see comparison of formation depths for different lines in each pair, made by Lena Homenko and Kalados about 10 years ago. And you see that normally we have this difference in each pair of about tens of kilometers. Although for this classical 6301, 6302 pair, the difference is almost 200 kilometers. So it's very substantial difference, taking into account that 200 kilometers is very substantial difference in the photosphere. Obviously, the thickness of the photosphere is about 500 kilometers, and magnetic field can change by a factor of 2, 3, 4 within the photosphere. And the left panel actually shows the calibration curves. The lines are calibration curves we built for this pair. And the dots, blue dots, show actual data taken from MHD simulations. And you can see that the spread is very, very high. And the main reason for the spread actually is this difference in line formation. So there is a problem, and the problem is that we can't use the most common pair of spectral lines for intrinsic magnetic field diagnostics or for filling factor estimation. So what we did, we decided to look for other methods that can be used for alpha or for BReal diagnostics using this pair, simply because this pair is the most available pair for magnetic field diagnostics. So these three histograms show how spatial resolution affects distribution of parameters basically measured using the spectral lines. So you already seen the left histogram probably. So the black line shows magnetic field distribution measured using very high resolution, basically resolution equal to the resolution of the model. And bars actually show magnetic field distribution measured using a resolution equal to a spatial resolution of Hinode. So BF, or what we measure, changes very substantially simply because what we normally measure is actually flux. The middle panel shows MLR for this pair. Yeah, it changes not as much as actually measured magnetic field measured using one line, but still there is a substantial change. And the right panel shows as a parameter called Stokes V width, basically the width of Stokes V peak measured in 6301 line. Surprisingly, it also doesn't show a substantial change with the resolution. And that is why we decided to use it, to try and use it for diagnostics of filling factor and diagnostics of intrinsic magnetic field. So again, you see probably the same histogram on the left, and the right panel shows calibration curves for this parameter for 6301 line for different intrinsic magnetic field values. And the blue dots show actual data from MHD simulations. And what we can see, there are two main things which basically make this method different from magnetic line ratio. First of all, the spread of points is actually much lower. Why? Simply because this method is based only on one line, on measuring magnetic field, on measuring basically one parameter with one line. So we are not affected by different formation depths or formation heights. Another and very important difference is that if you look at calibration curves, for instance, for MLR method, they saturate. They're almost flat beyond 1 kilogauss, while this method, it doesn't saturate. Well, we checked it at least up to 2.5 kilogauss, and it's almost proportional. Basically, this parameter is almost proportional to intrinsic magnetic field. So this method actually looks much more promising than MLR. Another method I will probably I'll talk. So, and there is a third method. It's not really a method. We call it statistical method, but it's very trivial thing. Basically, it's based on this two-component structure of magnetic field I mentioned before. And if we assume that at a small patch of the photosphere, the intrinsic magnetic field is constant, then we can easily calculate the filling factor simply as a ratio of measured magnetic field to this assumed magnetic field, and how to determine the real intrinsic field. It's basically the maximum field we observe within this patch. So now let's compare the three methods. We used it for estimation of filling factor using this MHD simulations. And we can compare estimated filling factor now to the actual filling factor taken directly from simulation. So these four maps show the left top map show actual distribution of the filling factor, and three other maps show the filling factor estimated using these three methods. So of course they grasp the structure. However, we can see that, for instance, MLR normally underestimates the filling factor, while Stokes-Lewis method and statistical methods are quite noisy. Well, these maps are not very informative for a comparison, basically for figuring out the quality or reliability of this method. So what we did, we compared values estimated using these three methods with actual values taken from simulations. And again, you can see that MLR, magnetic line ratio method, normally underestimates filling factor. And also it doesn't work for blue dots. Basically, it doesn't work for low field values corresponding to granulation cells. Stokes-Lewis is much better. It works for intergranulation network and partially works for granulation cells, and also it doesn't underestimate the alpha values. Although for weak field, obviously, yeah, you probably can see that it defaults for very weak fields. I think for less than 200 Gauss, it just doesn't work. But we are not really interested in fields in measuring in pixels with field less than 200 Gauss, simply because most telescopes provide an error of about 100, 150 Gauss. Statistical method, of course, is the best, and probably the result. Well, it looks better than two others, but of course we should not forget that statistical method is based on very strange assumptions that the intrinsic field is nearly constant, and it requires a measurement not in just one pixel like two other methods, but in a range of pixels. So that's what about measurements of intrinsic magnetic field in the quiet photosphere. Now I want to show you a couple of slides related to measurements in solar flares. And in solar flares, it's completely different. This piece, it's another piece. It's based on our 2014 paper. So basically, we can't use magnetic line ratio for measuring, estimating intrinsic magnetic field or a filling factor, simply because, of course, during flares, spectral lines are affected by Doppler shifts. But basically, they are multi-component. They're affected by different various variable Doppler shifts. They have very different widths. They have Zeeman splitting, and most importantly, some of these components forming spectral line profiles in flares are in emission. We know that it's normally the case for chromospheric lines like hydrogen lines, calcium lines, etc., etc. But it's also the case for iron lines, which are formed much deeper in the photosphere closer to temperature minimum, but they're still affected. And as an example, these two panels show iron spectral lines observed during flare. So the left panel shows 5233 line observed in X-class flare very long time ago. There is a noise, but you can also see that there are some very interesting emission components, sort of little bumps at the wings. And the right panel, it shows this classical 6301, 6302 pair, also observed in flare, but using Hinode telescope. And it's very interesting because 6302 pair shows very strong emission peaks. And what is even more interesting that these emission peaks, they definitely show Zeeman splitting, and then Zeeman splitting is much is definitely greater, is definitely bigger than splitting of the main profile. And actually, you can see the same in the left profile, in this less sensitive 5233 line. The main profile, the main absorption profile almost not split. I mean, the splitting is probably like tens of million strands. But the emission components, they show very substantial splitting and also substantial Doppler shifts. So how do we work with solar flares if we know that line profiles are strongly affected by by several factors? So again, we can't use normal MLR simply because MLR, of course, uses certain calibration. This calibration is based on known line profiles. These line profiles are different. However, it appears that we can use MLR, but it's not just normal MLR. It's MLR using several spectral lines, again with different sensitivities. So we did some radiative modeling, basically assuming that the line is formed by two components. One component corresponds to very weak magnetic field, and another component corresponds to strong magnetic field and is an emission. And we found that again that we can actually calibrate our measurements to estimate the real magnetic field. So these panels show effective magnetic field values using three different lines with three different lambda factors. So the lambda factor close to 1 is this 5233 line, and two other dots correspond to 5247 and 5250 lines. And you can see that the magnetic field actually affects, the intrinsic magnetic field affects the shape of these lines, and they can be used basically to estimate the strong field or subtelescope, or what we call intrinsic field and filling factor. Another possible method is based on actually analysis of splitting of Zeeman splitting of spectral lines, but it uses basically it uses Zeeman splitting at different parts of spectral lines, from the core to up to the wings. And this method is called bisector method simply because what we measure effectively is the Zeeman splitting of these bisectors. Yeah. And then we can build what we call bisector splitting functions, basically which show how splitting of bisectors changes from course of spectral lines to the wings. So there are these two methods, and we decided to apply these two methods to, I don't remember why we chosen these three particular flares. I think they were probably the least noisy flares. As the data is obtained, we're using Kiev horizontal polar telescope, which is quite old instrument, and the noise is quite high. But these three events showed probably the lowest noise, so we decided to analyze this event. So here you can see basically the fitting of using these two methods. So we apply fitting to these three solar flares, and the left panel show fitting for bisector splitting functions. So actual lines are bisectors of three different lines, corresponding to three different lines with different magnetic sensitivity, and dots are fitted bisectors. They're fitted using two-component magnetic field structure with very weak ambient field and strong subtelescopic flux tube field. And the right panel, they show fitting of this multi-spectral line MLR method. Basically, we use three lines. Again, it's the same three spectral lines with different lambda factors. So as you can see, while fitting is, the quality is sort of mixed. The last flare probably the fitting for the last flare is probably the best, and the fitting for the last two flares is the best, while the first flare shows very substantial deviations, especially for the 5233 line. It's basically green lines on the left panels and this set of dots on the right panels. Still, we measure, still basically we sort of able to get some fits, and that's a result of this fits. What we are mostly interested is the filling factor here. Sorry, it was another paper, so we used letter F here. So it shows a filling factor and a value of the strong magnetic field component. So what is interesting is that the filling factor is very low. It is between 5 and 15%, and the intrinsic magnetic field is about like 2 or 3 kilogauss, which is of course very different from what we see when we just measure magnetic field using magnetograph. What we see normally is like a couple of hundred gauss. It's normally less than a kilogauss. But of course, the most interesting finding we finding in the analysis of flaring Stokes profile is what I mentioned at the very beginning: is that the spectral the profiles we see normally shows emissions, and these emissions actually correspond to much stronger magnetic field. So basically, there are two components. One component is an emission; it corresponds to stronger field, and one component is in absorption; it corresponds to much weaker field. And this table, there are the results of fitting. They also show that other parameters like a temperature, basically the right the last column on the right, and Doppler velocities are also very different. And there is very simple, probably very trivial physical interpretation. So again, if we go back to this classical picture of the lower atmosphere of photosphere and chromosphere, the interpretation is very simple. We just think that the emission comes from the intergranulation network, where the strong field is concentrated, and that's the magnetic field which is actually connected to the corona, and that's why this flux through the photosphere is responsible for the transport of the energy from the corona down to the photosphere, and that's why we see emission, higher temperatures, etc., etc. And patches of the photosphere which are not connected to the chromosphere, they normally show a much weaker magnetic field, ambient magnetic field. And this flux is not connected to the corona, it just forms a low-level magnetic canopy. That's why we don't see any high temperatures, we don't see high velocities, and we see absorption with very weak magnetic field. So that's summary for this a bit unrelated two pieces of research. So the main point, of course, is that photospheric magnetic field is very inhomogeneous, and what we measure is not magnetic field. Next time, when you use data from Hinode magnetograph or whatever, you need to remember that what we see is not real magnetic field. What we see is a flux per pixel. Another very interesting result, although it's not new, is this so-called magnetoconvective collapse. Basically, it means that magnetic field can have discrete components. So the distribution is not smooth. It can have like actual real strong component and basically and very weak magnetic field. So there are small scale flux tubes of very strong magnetic field embedded into much weaker ambient field. The next basically conclusion is about measuring this strong magnetic field or intrinsic magnetic field in quiet photosphere. We found that, well, normally people use magnetic line ratio, and we show that in addition to line ratio, there are two other methods. One of them, we never met them. We never met description of this method in any other study. So we think that we are first who showed this, and we show that we can use a so-called Stokes-Lewis method to measure this intrinsic field, and in a sense, it's better than magnetic line ratio because it doesn't saturate, and also it's based only on one line, so it can be used with this classical pair 6301, 6302, or just with any other line. You don't need a pair. And two other basically conclusions, they relate to flares. The first one is very general. Basically, magnetographic field measurements and flares are dangerous. We shouldn't really use them, especially at least during impulsive phase, basically, or whenever we see very strong emission in hydrogen or in chromospheric lines. Basically, it would indicate that there is some emission in deeper lines and in iron lines, so they're not really, they can't be really used for magnetic field measurement. However, we can use we can assume that the field in flares also has multi-component structure. And we can use fitting using two methods. Basically, one of them is similar to magnetic line ratio, but uses just more lines, and another one is based on fitting the whole Stokes profile to estimate the magnetic field. And we show that there are two populations of magnetic field. One corresponds to one normally shows emission, and one corresponds to absorption component, and they're physically separated. Basically, they correspond to different fluxes, different magnetic field conductivity, with different responsibility for energy transport in flares. Okay, so basically that's it. I was a bit probably chaotic, so yeah, if any questions, however simple, you are very welcome. You can ask questions in Russian.
Thank you, Mikola. Any questions? I have one question. Probably you told this, but please remind what are the expected smallest scales of magnetic field in corona and photosphere? It's down to what resolution we should count.
Okay,
that,
so
that
yeah,
the
in
field
the
become
photosphere, yeah. So in the photosphere, it's much more complicated question. It's completely out of scope of this research. It's about MHD in corona, and it depends if it's a shock. Obviously, scales can be, but in photosphere, it's a very good question. Actually, there is a slide because people always ask this question. So what about sizes? Yeah, I never mentioned it because we have no idea what sizes are. To measure sizes, basically, we need direct imaging. And of course, the methods we use have nothing to do with direct imaging. However, there are some measurements which can give us an idea of what are the sizes of the small-scale intense flux tubes in the photosphere. There are different estimations ranging from from direct imaging in near infrared. People used, I think, spectral interferometry, and they found that this flux tube should have a scale of about 100 kilometers. However, some estimate other indirect estimation, but they are very are estimations based on observations, very high resolution observations of coronal rain. It's basically after flares, plasma sort of moves down to the photosphere when during cooling process, and they resolve elements with a thickness of about few hundred kilometers. So probably it's the upper limit for the size of this element. But there are much smaller estimations. Basically, there are some estimations showing that this element should have sizes of about like 50 kilometers. So of course, if sizes are so small, there might be some physical implications because obviously the smaller is a length scale, the faster should be dissipation, just even with normal resistivity. But so it's very open question. But yeah, basically this question is non-answered, and the upper limit is probably a few hundred kilometers.
I see. Okay, no questions. Okay, if there are no more questions, we should thank the speaker. Thank you, Mikola, for a very interesting presentation.
Thank you.
Yep. Yes. Bye.
Okay, so should we
Okay. So
end our meeting? Okay. Thank you and goodbye.
Thank you. Bye.
Goodbye.
Bye.